Okay, now let me discuss about the computational model in embedded systems. So now actually what are the several ways we can compute the problems or compute the formulas or compute any kind of situations in the embedded systems. So there are different types of models we have in our embedded systems. The first one is the data flow graph model, control data flow graph model, state machine model, sequential programming model, concurrent process model, object oriented model. So now these are all the models where these models can do the computational in the embedded systems. Now let me go to the first one, the data flow graph model. So in the data flow graph model, it is as like the similar things what we look like in our flow chart. When we write a flow chart, we write in a descripted way. The first step of data will go to the next step, and there some computation will happen. And the further on, it will go to the next step. Will be indicated either by the circles or by the hexagonal shape or by the square shape, something like this. Correct. Now, this is how the something like called as a visual mode in which the operation of data is represented using a block, circle, and data flow is represented by using an arrows. That is what we have. We have written the flow chart also, right? So now this data flow graph model is a data-driven model in which the program execution is determined by the data. This model emphasizes on the data and operations on the data, transforms the input data to the output data. Now, this is how the data flow model is. Right. Now, we'll see exactly what exactly you mean by the data flow model and so on. Let me go with one example. I want to compute one operation, arithmetic operation, x equals a plus b and y equals x minus c. Now, there are totally four variables are used, sorry, five variables are used, a, b, c and x, y. These are the four variables used. Now, first thing I am going to compute a plus b and the result is stored in x. So, how to represent that? Now, this is an variable a, this is an variable b, and inside the circle, whatever the computation I should do, the arithmetic computation, I use an plus here. So now when I combine with these two, a plus b is happening here and that results to x. Now x is used here. Now I want to do one more computation, that is x minus c. So I'll take one more variable c, and since here the subtraction computation I'm doing, I should use minus here. So x minus c results me y. That is what the final result is y here. Now this is what we call it as data flow model, in which it will easily understands how actually the data will be flown from top to bottom. Now the next type of model is control data flow. In the previous case, we just done the computation without having any condition. But in this case, we'll do any kind of computation by using only the some few conditions. If that condition is true, I'll perform this computation. If condition is false, I'll perform another computation, something like this. So now this is what we call it as conditional or the control data flow. Control data flow is all done by used on some few conditions. Now this now control DFG is used for a modeling application involving conditional program execution. Now CDFG model contains both data operations and control operations. So now in the previous case we had only the data operations, there was no control in this side. But now in this present thing we have both control operations as well as the data operations. Now in this case CDFG uses both data flow graph as element and conditional as decision makers, right? Now if flag equals 1, then x equals a plus b, else y equals a minus b. Now the condition what here? Now I want to check whether my flag is equal to 1 or not. So in order to represent this, this is how the thing we are looking for. Now in order to check the condition, I want to use the diamond shape block, so where it represents the checking of the condition. Now this checking of the condition will be having the two outputs, the true one, the true side, the other one is false side. Now if flag equals 1, if it is true, it will come in this direction. If it is false, then it goes in the other direction. Right. So in this case, I will be computing the things. If now flag equals 1, I am performing x equals a plus b. Now if flag equals 1, if it is true, I am performing a here, b here, a plus b, right? If it is false, then I am performing a minus b. So I can see here now a here, b here. If it is this false, then I am doing a minus b. Now this is called as conditional data flow model. Coming to the next one, the state machine model. Now the state machine model is reactive, or it is an event driven embedded systems. As I told in the previous case, what I mean by event driven, if any event occurs, then for that event I should perform some actions, that is called as event driven system. Now there are three things are there in this state machine model. There are three things: events, action, and transitions. The actually states, events, actions, and transition. Now, what do you mean by state? State is a representation of the current situation. Now, I'll go with the example. In the next slide, we'll go with an example and explain all these things. What do you mean by state, what do you mean by event, and so on. Now, an event is an input to the state. Okay, an event is an input to the state. The event acts as stimuli for the state transition. Well, now, what do you mean by transition? Transition is the movement from one state to another. What do you mean by action? Action is an activity to perform by the state machine. Now, let me take one example. If I want to visit a bank, now first I will enter a bank either to deposit the amount or withdraw the amount or with some other kind of function I want to go to a bank. Now, when I enter a bank, either I'll be standing in a queue or either I'll be doing depositing the amount there. Now, there are different types of state. If I'm standing in the queue, that is called as waiting state. That is one state. If I'm performing some depositing of an amount, that is called as one more state. If I'm returning back, that is called as one more state. Now, whatever it is, at any given amount, at any given time, I'll be standing in one of the state, either in the waiting state or either I'm depositing the amount. Now, what do you mean by an event? Event is an input to the state. Now event means what I'm doing now. I'm standing in a queue. What I'm doing, I'm idle. I'm idle here. I'm simply idly standing on the queue. If I'm depositing something amount, then that means I'm not an idle. I'm doing some action there. Now, what I mean by transition? Transition means if I go from my waiting state to the depositing to deposit the amount, that is called as transition. That means from I'm moving from one state to other state. That is called as transition. Now, what I mean by an action? I'm performing some action. I'm depositing the amount or I'm withdrawing the amount. That is called as action. Now, I hope this gives you a clear picture to understand what I mean by state, event, transition, and action. Now, coming to the next kind of model, that is finite state machine model. Now, in this model, we explain with one of a very good example. If suppose in our car, if you have not fastened our seat belt, then there will be warning will arise from the car, which is all due to our embedded systems. When I start my ignition in the car, it will wait for 10 seconds after ignition. If not, if my seat belt has not fastened, if I have not tied my seat belt, then the alarm signal will generate. Right? Now this is some few actions will be taken care based on some events. Now for an example now when the vehicle ignition is turned on and the seat belt is not fastened within 10 seconds of the ignition on, the system generates an alarm signal for 5 seconds. Now, alarm is turned off and off when the alarm time expires, or if the driver passenger fasten the belt, or if ignition switch is turned off. Now, if suppose even after the ignition on, after 10 seconds, I didn't fasten my seat belt. Now, for 5 seconds, for the next 5 seconds, it will generate a alarm signal. Now, after within that 5 seconds, if I fasten my belt or if I turn off my ignition, then that alarm signal will goes off. Or if suppose if my I didn't tied my belt, or if I didn't turn off my ignition, if my 5 seconds will go on, then automatically the alarm signal will get off. Now these are the some few conditions it has been set in the embedded systems inside the car. Here the states are alarm off. See here you can see the different types of states here. The states are alarm off, waiting, and alarm on. These are all the three states of the alarm. And the events are ignition key on, ignition key off, time expire, alarm time expire, and seat belt on. Now, now using my finite state machine model, I can represent the same scenario by using this diagram. Now this is the alarm off, this is the waiting state, this is the alarm on. Now let me come to alarm off. From alarm off, if suppose my ignition key gets on, then it will go to a waiting state. It will wait for 10 seconds. If my ignition key becomes off, my alarm will also become off. If my if I fasten my seat belt, then my alarm will again get off. Now from this waiting state of 10 seconds, now the alarm will ring for 5 seconds. If that 5 seconds will exceed, then again my alarm will become on. Now when I switch on my ignition key on, it will wait for 10 seconds. Now when that time 10 seconds get expired, then my alarm will get on. During this alarm on, if my alarm time expires, then alarm become off. Or if I fasten my belt, then also alarm will get off. If my switch on my ignition key, then also alarm will become off. So this is how I represent the flow diagram by using the finite state machine model. Now this is one more way of the timer, how exactly the timer will work. This is how I have written here. Now suppose this is an idle state, ready state, running state. Now I have loaded the timer now. Okay. Now the timer is on. I have started my ignition. The timer is on now. It should count for 10 seconds. Now when the 10 seconds is counted, now this will get ready. That means now my alarm will get on. Now that on will start the timer and it will start running. It should generate the alarm signal for 5 seconds. So it will start the timer. It will decrement the count from 5, 4, 3, 2, 1, 0 until that time the alarm will be running. Now once from the running state, again if it wants to become idle, then either my stop timer should expire its time, or there should be some timeout interrupt should occur, then only it will go to idle state. Now this is how I can represent this alarm off condition and the timer on and off condition by using finite state machine model. Now this is one of the case study example one I have taken it for in order to know about automatic tea coffee vending machine. And one more example also I have taken here. Now the next model is the sequential programming model, where this sequential programming model is a very simple. It will go on running according to the sequence. That means step by step execution will be happening. So in this, the functions or processing requirements are executed in sequence. It is same as the conventional procedure programming. Here the program instructions are iterated and executed conditionally, and the data gets transformed through a series of operations. So in order to represent this, I can use the flowchart itself. So this is what we call it as sequential program model. Now this is the flowchart in order to represent my seat belt fasten when the ignition is on and off. The next one is concurrent communication processing model. So in this case, what we do is that we have concurrently executing task process. In the case of sequential execution leads to a single sequential execution of task and thereby leads to poor processor utilization. When the task involves input output waiting, sleeping for specified duration, etc. This was the things which was happening in sequential. But in case of concurrent, my processor will start executing parallelly. So that is what we call it as concurrent process. This is the example, same seat belt process. I have taken how actually this can be executed concurrent processing model. Now in this concurrent processing model, we should divide it into several steps. The first step is timer task for waiting 10 seconds. That is one task. Task for checking the ignition key status. Third task is task for checking the seat belt status. Task for starting and stopping the alarm. Alarm time task for waiting for 5 seconds. Now, based on this different five tasks, now I do the concurrent process execution or the parallel execution process. Now, this is how I have written here how to do the concurrent process step by step. Now, the last one is the object oriented model. Now, we all have studied the hoops. We know what we mean by object oriented model. In this object oriented model, each one is treated as an object here. Each one is treated as an object. Now, based on this object, we try to do the model by implementing this seat belt in a car. Now, this is how we will work with different types of models in case of embedded systems.